Welcome to the class of stochastic processes, tracking the number of HIV infections. This is a very good example that teaches how the number of HIV positive patients can be estimated. We know that the incubation time from the time when an individual becomes infected with the HIV virus until the symptoms of the disease appear is very, very long. As a result, it is difficult for public health officials to be certain of the number of members of the population that are infected at any given time. And this is the first approximation model for this phenomenon. We suppose that individuals who contract the HIV virus is in accordance with the Poisson process with rate lambda, and lambda is unknown. Further suppose that the time from when an individual becomes infected until symptoms of the disease appear is a random variable having a known distribution G. Suppose that the incubation times of different infected individuals are independent. Now, we let N1T represent the number of individuals who have shown symptoms by time T, and N2T represent the number who are HIV positive but have not yet shown any symptoms by time T. So every patient who have contracted HIV virus can be divided into two categories. The first category is those who have shown symptoms, or the second category refers to those who have not shown symptoms. And suppose that the number of people who contract the HIV virus is a Poisson random variable with parameter T, parameter lambda, and also the time from individuals become infected until symptoms of the disease appear is a random variable following distribution G. Now, if a patient who have contracted the virus at time S would have the probability of GT minus S that will show symptoms by time T, because we know that the time that from individual becoming infected until the symptoms of the disease appear is a random variable by distribution G. So GT minus S denotes the probability that this individual will have shown symptoms by time T. So based on the proposition we have learned previously, we know expectation N1T will be equal to lambda times integration 0 to T GT minus S. And expectation of N2T will be equal to lambda and 0 to T G bar T minus S, because the patient can either show symptoms or not show symptoms, right? So if this probability is GT minus S, and the probability that it will not show symptoms will be 1 minus GT minus S, which is G bar T minus S. Now, we need to estimate lambda, because lambda is unknown. But now, because the number of individuals who have exhibited symptoms by time T must be known, because those patients may go to the hospital to seek help. So usually we will know the number of patients who have exhibited symptoms, right? So suppose N1 is known. So N1 is actually equal to expectation of N1T, and that is lambda times integration from 0 to T G y dy. So we can estimate lambda by N1 divided by integration 0 to T G y dy, right? So basically you just move this to the left hand side, right? And how about N2T? Because now we already know lambda bar and lambda head, right? Because we have estimated lambda. So we can just plug in lambda head into this equation, and turns out that this is how N2T becomes. So just to give you a more solid example, if G this is just an example. If G is the exponential distribution with mean mu, then we know that G bar Y is equal to e to the power of minus y over mu. So we can now calculate n to t by the denominator is from integration from 0 to t, gy dy, and gy would be 1 minus e to the minus y over mu dy, right? And the numerator will be n1, the integration 0 to t, and e to the minus y divided by mu dy, and that will be the result. And to be more specific, if we are looking at the time horizon, for example, 16 years, and if we have known that mu is equal to 10, and n1 is equal to 20,000, and we can really estimate n to t, and based on this equation, and the result will be to 18.96 thousandths. Another example, insurance claims are made at times distributed according to a Poisson process with Renewal, and the successive claim amounts are independent random variables having distribution G with mean mu, and are independent of the claim arrival times. Now we let SI and the CI represent the time and amount of the I claim. So the total discounted cost of all claims made up to time t, represented by dt, can be defined as summation CI. Remember, CI represent the amount of the I claim, right? But we want to so basically you can think of that way. If this is from 0 to t, and those are claims, insurance claims, and basically, so for example, this is the S1, this is S2, this is S3, okay, this is for time, and C1, C2, C3 represent the amount, right? So basically, for every insurance claim, we want to discount it back to time zero. So you kind of have to multiply by CI multiplied by e to the minus alpha SI, because you discount it, every claim are discounted back to time zero. Okay, so that is dt, and of course alpha is the discount rate, and I from 1 to nt, and nt is the number of claims made by time t. Now recall that CI, this amount, is a random variable, right? And also SI is a random variable. NT is a random variable too. So we, of course, can seek the expectation of DT, because DT is a random variable for sure. Okay, expectation of DT would be equal to expectation of DT conditional on NT is equal to n times the probability of NT is equal to n. And because NT is a Poisson random variable, so that would be e to the minus lambda t to the power of n divided by n factorial. And we take summation n from 0 to infinity. Okay, now we look at this. Expectation of dt conditional on nt is equal to n. Because we know that this is actually based on the proposition we learned previously, we know that given the number of the arrivals, the dt, the summation dt is equal to summation ci e to the power of u alpha times u of I. Okay, because given that we have known the number of arrivals, and then the SI's distribution is actually order statistics, uniform order statistic, right? So we like U and the little bracket I to represent the uniform order statistics. So that will be summation CI times e to the minus alpha U of I. Okay, so I can bring the summation outside the expectation. So summation expectation Ci e to the minus alpha u of I. And because Ci and the u of I are actually independent random variables, so the expectation can be separated, right? So we have summation expectation of Ci times expectation of is e to the minus alpha u of I. And we know u of I is uniform random variable from 0 to t. Okay, so here I made a remark to make sure you know that this equality is because S1, S2 up to Sn has the same distribution as the uniform order statistics. Now, because we know expectation of Ci is equal to mu, so we know that expectation of dt conditional on nt is equal to little n is equal to mu times summation expectation of e to the power of minus alpha u of I. Okay, now if I bring the summation inside the expectation, then we have mu expectation of summation e to the power of minus alpha u of I. But u of I represent order statistic, right? And you take summation here. The order statistic with or without, if you take summation, if the statistic is order or not, is not important at all, right? So summation of order statistics is equal to summation of unordered statistics. Remember, pay attention to this UI. This UI is without bracket, right? So that means this UI are just uniform random variables without being ordered. But summation of ordered statistics is the same as summation of unordered statistics, right? Unordered random variables. Okay, I make sure. So this equality is because order statistics U1, U2 up to UN are the values of U1, U2. So this is unordered. So that is increasing order, and therefore the summation would be the same, right? So this equality would just hold here. Okay, we continue the derivation. So we have expectation of dt conditional on nt is equal to n is equal to n mu times expectation of e to the power of minus alpha u. Now I use u because, look at here, because this ui is uniform random variable, right? IID, so I could just use u to represent uniform random variable. And so because they are IID, so summation of expectation minus alpha u will equal to n, and so I can n e to the power of minus alpha u, and I can move n outside the expectation, so I would have this, a mu expectation of e to the power of minus alpha u. And e to the expectation of e to the power of minus alpha u is equal to 1 over t times integration from 0 to t e to the power of minus alpha x dx, right? This is expectation of e to the minus alpha u, right? Okay, so we get the result like this. And this is when nt is equal to n, so we have n here. Now, if we have nt, then obviously we have to replace little n by nt, right? So we have this result. Okay, so expectation of dt is equal to expectation of dt conditional on nt. Okay, so we take expectation on this. Okay, and we know that that is expectation of nt, that is lambda t. Expectation of this, that is the same, because this is a constant, right? So we get the final result, like lambda mu over alpha times 1 minus e to the minus alpha t. Another example, an optimization example. Suppose that items arrive at the processing plane in accordance with the Poisson process with Renewal, at a fixed time t, all items are dispatched from the system. And the problem is, how can we choose an intermediate time, little t, between 0 and t, at which all items in the system are dispatched so as to minimize the total expected weight of all items? So this is like you have 0 and a t, and then some items just come in accordance with the Poisson process. Now you want to choose little t here, little t here, and to make sure that the total weight of all items is minimized. So if the little t is chosen here, and remember from 0 to little t, those items actually arrive in accordance with the Poisson process, right? So basically, based on the knowledge we know about Poisson process, all the items are actually homogeneous and can distributed uniformly between 0 and t. So basically, we know that the wait time of the items within 0 and little t should be on average t over 2, right? And how many items can arrive between 0 and little t? That would be lambda t. So on average, that would be the total weight, right? So lambda t times t over 2. That is before little t. And how about after little t? So I mean from little t to capital T. And we know that the number of items that would arrive between little t and capital T would be lambda times the capital T minus little t, right? And similarly, the wait time of each item would be capital T minus little t divided by 2, right? So that would be the expectation of total weight of all items. And of course, you can use integration to get the same result too. But intuitively, this is very intuitive, right? If you, based on the knowledge we know about the Poisson process, we can, without using integration, we can just write down the expression like that, right? Okay. And then it follows that we just take derivative with respect to t and make it 0, and you can solve. Without any surprise, little t would be equal to t over 2. So meaning if you have, for example, 0 to 10 hours, then what time should you choose to dispatch? It should be 5, 1/2. So just in the right middle, right? Now, homogeneous Poisson process. The arrival rate is a function of t. So previously we talked about Poisson process, which we mean homogeneous Poisson process. So the lambda is actually a constant. Now, when we talk about non-homogeneous Poisson process, we mean lambda can be a function of t. So we are talking about lambda of t. Okay? So still, we have a counting process, NT, like Poisson process. And the NT is said to be a non-homogeneous Poisson process with intensity function lambda t if, number one, n of 0 is equal to 0, meaning the system starts from 0, okay? Number two, n2 has independent increment. This remains the same, right, like the Poisson process. Number three, in a very short period of time, the number arrival that is greater than or equal to 2, this probability is actually equal to little o of h, which means 0 when h is very, very small, right? And number four, then the probability that in a very short period of time, and there's a arrival, this probability is proportional to the length of the period of time, right? But there's one thing different. Previously, we have lambda h. Now we have lambda th, because recall that now the arrival rate is a function of t, right? So we have lambda of th plus little oh, but we know that when h is very small, little oh is simply equal to 0 or very, very close to 0. Proposition. Let NT and MT be independent non-Poisson non-homogeneous Poisson processes with respective intensity functions lambda t and mu t, and let n star of t is equal to lambda t plus m of t, then the following are true. Number one, n star of t is a non-homogeneous Poisson process with intensity lambda t plus mu t. Previously, we talked about if two Poisson processes are put together, we have a grand Poisson process with lambda plus mu, right? But now, if we have two non-homogeneous Poisson processes putting together, we still have a grand non-homogeneous Poisson process with parameter lambda t plus mu t. So non-homogeneous Poisson process plus non-homogeneous Poisson process would be a non-homogeneous Poisson process, just like homogeneous Poisson process plus homogeneous Poisson process would be equal to a homogeneous Poisson process. And given that an event of the grand Poisson process n star t occurs at time t, then independent of what occurred prior to t, the event at t was from nt process with probability lambda t over lambda t plus mu t. We have learned this previously, right? Okay. So one more proposition. Let nt be the number of events of the non-homogeneous Poisson process by time t with the bound intensity function lambda t less than or equal to lambda. So nt follows is a Poisson process with mean expectation of nt, and we know this is equal to lambda times the integration from 0 to t pi s ds. And the probability pi of s is actually equal to lambda y over lambda, right? So we can cancel out lambda and we get integration lambda y dy. And also this notation nt plus s minus ns means starting at time s, the number of events in its first t time unit. Okay, so basically that means the events that happens between s and the t plus s. So the period of time, the length of the time is t, right? So basically expectation of nt minus s minus ns, that means the arrivals between s and the t plus s, right? And that is equal to, you just take integration from 0 to t because the length of time is t, right? And the lambda s plus y dy. Okay, for example, y start from 0, so that means the system starts from s, right, up to t. So the system is terminated at time t plus s. Okay, so that is just like s to s plus t integration, s to s plus t lambda y dy. And actually, we have a notation m of t, which is defined as integration from 0 to t lambda y dy. It deserves a special name called mean value function. I give you a very simple example here. We have a hot dog stand, okay, that opens at 8 a.m. so basically from 8 to 11, these 3 hours period of time, customers seem to arrive on average at a steadily increasing rate that start with an initial rate of 5 customers per hour. Okay, so it turns out that from 8 to 11, we will reach a maximum of 20 customers per hour. Okay, and then from 11 a.m. to 1 p.m., this rate, okay, seems to remain constant at 20 customers per hour. Okay, but this arrival rate can drop steadily from 1 to 5. Okay, so up to 5, the value would be the lambda would be 12 customers per hour. And we assume that the number of customers are independent at disjoint time periods. Now, what would be the good probability model for this phenomenon? Obviously, Poisson process, right? But what is the probability that no customers arrive between 8:30 to 9:30? Okay, and what will be the expected number of arrivals in this period? So from 8:30 to 9:30, so basically first we can just derive the lambda of t, right? So basically based on the description of the problem, we look at this picture. So from 8 a.m. to 11 a.m., we start from 5, right? And steadily increase up to 20, right? And from 11 to 1, the assistance, the rate remains constant at 20, right? And drop from 20 to 12, from 1 p.m. to 5 p.m. So that would be the lambda of t. So this would be 5 plus 5t, right? So t would from 0 to 3, right? 0 means the time 0, which means the season start at 8 a.m., right? 11 means after 3 hours, right? So after 3 hours, we have 5 plus 5 times 3. So that would be 20, okay? And the system remains at 20. The hot stand remains at 20. Lambda is equal to 20, right? And the drop, okay? So we can derive the lambda of t like this. Okay, so n of t would be the number of arrivals during the first t times that the store is open. So basically, what about the number of arrivals between 8:30 to 9:30? Okay, so basically it should be, okay, this would be like, let me write this, 1/2 to 1/3, and 5 plus 5t, then dt, right? Okay, and so this would be the first question, okay? And the second question is, what about the probability that during this period the number of customers is 0? So that would be, so this should be, I think this should be 10. The result will be 10. So probability that in this period of time the number of customers is equal to 0 would be e to the minus lambda, because lambda is equal to 10, times 10 to 0, because 0 customers, right, divided by 0. So that would be e to the minus 10. Compound Poisson process. A stochastic process xt is said to be a compound Poisson process if xt is defined as yi, summation yi, I from 1 to n of t. And where nt is the Poisson process and yi is a family of independent and identically distributed random variable that is independent of nt. A very special case is when yi is equal to 1, because when yi is equal to 1, basically xt is equal to summation I from 1 to nt 1, right? So that would be nt. Okay, and we know nt is the Poisson random variable. So we have a proposition like this. xt is the compound Poisson random variable with Poisson parameter lambda t. And the expectation of xt is equal to lambda t times expectation of y1. And variance of xt, so remember xt is the compound Poisson random variable. That is equal to lambda t expectation of y1 squared. And what would be in what scenario this compound Poisson process can be used? I just give you an example here, like bus arrivals. If bus arrivals are Poisson distributed, then the number of passengers who have arrived by time t would be compound Poisson random variable, because we can just use summation. So yi means we can let yi represent the number of passengers in the I bus, right? And the bus can from 1 to nt, because bus arrival can be a Poisson random variable. So totally that would represent the total number of passengers that arrive by time t, and that would be a compound Poisson random variable. But why this proposition, expectation of xt is equal to lambda t, expectation of y1, and variance of xt is equal to lambda t, expectation of y1 squared? Why is that? Recall that previously we have done this. Expectation of summation xi, if n is a random variable, will be equal to expectation of summation xi conditional on n is equal to n. Then we take expectation with respect to n. Right? Okay? So inside the expectation, we have expectation of summation xi, that will be n expectation of x. So if we replace little n by capital N, we can replace here little n by capital N here. And we can take expectation with respect to capital N. So that would be expectation of n, capital N, times expectation of x. Okay? So that explains why expectation of capital N, nt, would be lambda t, right? And expectation of s would be expectation of y1 here. Similarly, you can just follow the same logic to derive variance of summation xi from 1 to n, and based on this equality. Okay, so you can calculate variance of the summation xi conditional on n. Okay, that would be n variance x. And you can also calculate this expectation of summation xi conditional on n. That would be n expectation of x. So you just put this back in here, the expectation and the variance in, just put it back in here. So we will have expectation of n variance x plus variance of n expectation of x. So that would be, because n and the variance x is actually constant, so you can move it outside the expectation. So you have expectation n times variance x. And also, expectation of x is constant here, so you can move it outside the variance. But variance, you have to take square, right? Outside the variance, you have to take the square. So you have expectation square of x times variance n. Okay? So putting everything together, you know that expectation of n would be lambda, right? Times variance x plus variance n would be lambda again, right? Times expectation of expectation square of x. So totally we will have lambda times expectation of x squared. Example, suppose that families migrate to an area at the Poisson rate lambda is equal to 2 per week. And if the number of people in each family is independent and takes on the value 1, 2, 3, 4 with respective probabilities 1/6, 1/3, 1/3, 1/6, then what is the expected value and the variance of the number of individuals migrating to the area during a fixed 5-week period? So we are looking at a 5-week period. So basically, we just use this proposition here. We use this proposition. Okay, so expectation of xt is equal to lambda t. Recall that now the t, little t will be 5 weeks, right? So lambda times 5, expectation of y1. So you kind of have to, so if we let yi represent the number of people that is I family, you just have to calculate expectation of yi first, okay? And that would be 5/2. And you calculate expectation of yi squared, and that would be 43/6. Then based on the proposition we just learned, we know that expectation of x5 would be lambda times 5, because we are looking at 5 weeks, right? Times 5/2 expectation of y1 or yi, right? Turns out we get 25. Similarly, variance of x5 would be lambda times t times expectation of y1 squared or yi squared. Okay, it doesn't matter because yi are IID random variable, so you can just look at it, yi squared or y1 squared, right? And that would be 43/6. So we get 215/3.